Since solving thermodynamic problems involves looking at changes in systems, every problem that we solve will be expressed mathematically in terms of a differential expression. So there are a few basic mathematical moves that we will use in working with these differential expressions. Let's look at them now. Typically, we will be interested in changes in state functions of the system, such as the energy. Remember that the energy for a closed system is a function of temperature and volume. So if I want to express a change in the energy, I have to add up the effect of changing the temperature of the system at constant volume plus the effect of changing the energy with respect to volume at constant temperature. Let's imagine that we want to look at how the temperature changes with volume at constant energy. If I keep the energy constant, then dE is equal to 0. And so I can write 0 is equal to how the energy changes with temperature at constant volume, dt, plus how the energy changes with volume at constant temperature, dV, remembering that my dt and dV are at constant E. Now I'm going to use a shortcut that we often use. So let's rearrange this equation. Minus dE dt at constant V dt is equal to dE dV at constant T dV. And although I can't actually divide through by a differential, because differential quantities are very small and go towards 0, so I can't divide by 0, it will always work for us if we treat these as algebraic quantities. So we can further rearrange this equation, treating the differentials as algebraic quantities, to get the partial of temperature with respect to volume at constant energy. And when I do that division, I get a partial derivative because I've kept the energy constant. That will be equal to, just doing the algebra on the above expression, the partial of energy with respect to volume at constant temperature divided by the derivative of energy with respect to temperature at constant volume, and it's the opposite of that. So the derivative of temperature with respect to volume at constant energy is the opposite of dE dV at constant T divided by dE dt at constant V. And that is the relationship between the three variables E, T, and V. Sometimes we will have a differential expression for our state variable. So for instance, a small incremental change in the internal energy can be expressed as T times a small incremental change in the entropy minus the pressure times a small incremental change in the volume. If I want to calculate how the energy changes when I change the volume of the system at constant temperature, then I will need an expression for this partial derivative. So we'll use the shortcut that we just learned and treat dV as an algebraic quantity. So if I do that at constant temperature, I can divide the above expression through by dV to get ds dV constant T times T minus pressure times the derivative of volume with respect to volume at constant temperature. But the derivative of volume with respect to volume is just 1, and so my change in energy when I change the volume of the system at constant temperature will be equal to the temperature times the change in entropy with respect to volume at constant temperature minus the pressure. Let's look at another example. Perhaps I want to look at how the energy changes as I change the entropy at constant volume. So in this case, the volume is constant, so dV is equal to 0, and that last term vanishes. So dE ds at constant V will be equal to T times ds ds at constant T, but ds ds is equal to 1, and so we find that the derivative of energy with respect to entropy at constant volume for a closed system is equal to temperature, which is just the expression, the definition of temperature, which we got at the end of chapter 2. Finally, let's look at how we can use the fact that the mixed second partial derivatives are equal to derive some useful expressions from our differential expressions for the free energy. So our differential expression for the Gibbs free energy is dG equals minus S dt plus V dP. I can find the first derivatives of this expression by treating dt and dP as algebraic quantities. So the derivative of Gibbs free energy with respect to temperature at constant pressure is minus S. Likewise, the derivative of Gibbs free energy with respect to pressure at constant temperature is the volume. Now, I want the mixed second order partial derivatives, and so I need to take the derivative of these first derivative expressions, but change the variable that I am taking the derivative with respect to. So in the second expression, I will now take the derivative with respect to temperature, and in the first expression, I'm going to take the derivative with respect to pressure of the derivative of G with respect to T at constant P. The second derivative will be at constant temperature. And since I've taken the derivative of the left-hand side of that first derivative with respect to pressure, I need to take the derivative of the right-hand side with respect to pressure, which gives me minus the derivative of S with respect to P at constant T. Now I can do the same thing for the other first derivative, which gives me the derivative with respect to temperature of the derivative of Gibbs free energy with respect to pressure at constant temperature. Doing the second derivative at constant pressure is equal to the derivative of volume with respect to temperature at constant pressure. And since this is a state function, the mixed second order derivatives are equal, and so I can set the derivative of entropy with respect to pressure at constant temperature equal to the opposite of the derivative of volume with respect to temperature at constant pressure. This is a very useful expression because if I want to measure how the entropy changes when I change the pressure of the system at constant temperature, I need only measure in the lab how the volume changes with respect to temperature at constant pressure. The right-hand side of this equation is all in terms of quantities that I can measure, and so I can go into the lab and make measurements of volume and temperature at constant pressure and use those measurements to calculate a change in the entropy.